Okay, so in the second part of 3.4, it involves solving log equations. And if you take a look at the guidelines, they're almost similar, if not near identical, to the guidelines for solving exponential equations. In general, right, you want to isolate the log if possible, if necessary. And after you get the log by itself, sometimes you either use the one-to-one property. Now, I didn't really call it the one-to-one property when I introduced it to you. I call it the property of equality for logs. This is basically your one-to-one property, okay? So it's also called property of equality of logs, which basically states that if you have a single log on both sides with the same base, this statement is true if and only if, right, x is equal to y. So basically you set the arguments equal to each other if you have a single log of the same base. Sometimes you can't always use the one-to-one property. You might have to use the inverse property, right? And the inverse property is basically exponentiating by whatever base that this log is. In this case, the base is just b, okay? You have to do that to the left and to the right side. And this is kind of important, okay? This is where it slightly differs. Sometimes you might end up with a solution that might be extraneous, okay? So extraneous just means extra, and it's just one of those weird things that when you solve a log equation, sometimes the answer doesn't plug back into the original equation, and usually what ends up happening is that it makes the argument negative, and you know that you can't have an argument within a log that's zero or it's negative, so make sure you check it back into the original equation, and I will show you that in the examples. All right, so let's work our way through maybe 4 examples here in this video, and then maybe another 3 or 4 in another video. Okay, so this first one right here, right, we're asked to solve or write the exact solution, so no calculator answer. So if I take a look at guideline number 1, right, what I want to do is get this log right here by itself, okay? So, you know, if you remember your basic arithmetic, right, I'm going to add 1, and then divide by 2. Okay, so over here I'm going to get 2 log base 3 of x minus 2 is equal to 8. And I have 8 divided by 2, which is 4. Now I have the logarithm by itself. And from this line, right, so if you remember the previous video on solving for the x-intercept of a logarithm, for a logarithm function to graph, from here, right, you can use your inverse property. Okay, so way 1 will say inverse property. Or way 2, you can directly, convert from log form to exponential form, okay? So using my inverse property, right, I would exponentiate both sides by base 3. So whatever I do to the left, I do to the right side of the equation. And way 2, right, kind of just bypasses the inverse property. You can just say, well, this is just 3 to the 4 is equal to x minus 2. Okay, so does it matter which method I use on a test? It doesn't, okay, but I would recommend that you use the inverse property, okay? It's just to practice this, right? This becomes x minus 2 is equal to 3 to the 4th, and you end up with the same statement on both sides. Okay, so 3 to the 4th, of course, is 81, right? 81 plus 2 is 83. You will also get x is equal to 83 if you do it, just converting it directly. So again, I would practice the inverse property just to show more work, okay? All right, so there is example 1. I've isolated the log, and I've used the inverse property. What if you have an ln in your equation? Let's say it's something like this. 3 minus 4. ln, the square root of x plus 1 is equal to negative 7. Again, I see a log, right? Whether it's base 3 like the previous problem, or in this case, the base is e. I still need to get this logarithm right here, right, by itself. And so I would subtract 3 on both sides first. All right, if I subtract 3, I'm going to get negative 10. And then divide both sides by negative 4. Okay, so if you divide both sides by negative 4, you're going to end up with positive 5 over 2. Okay, so from this line right here, you can recognize that you're going to, you've had the logarithm isolated. You want to use the inverse property. So exponentiate both sides by base e. So ln the square root of x plus 1 is equal to 5 over 2 exponentiate by base e, right? And so when you exponentiate by base e, this cancels out to the square root of x plus 1 is equal to e to the 5 over 2. And now you have a square root equation. X plus 1 square root is the same thing as x plus 1 to the 1/2. And again, this is good practice for solving equations with rational exponents, right? To get x by itself, I need to exponentiate both sides by base 2 now. Okay, so this is going to cancel out. You're going to get x plus 1 is equal to e to the 5th, and x is equal to e to the 5th minus 1. Okay, so this is going to check back into the original. And what I mean by check back into the original, if you plug this back into the original equation, right? I mean, e to the 5th, you know, if you enter that on your calculator, let me just see what the approximate value is. E to the 5th, let's see, e to the 5th, it's probably going to be 32 something, right? 148 something, I should say, minus 1. The approximate value, right, is about 147.4. And if you plug this in, right, it's not going to make the domain, the argument is not going to equal a negative number. And that's really what you want to check, okay? So back to the first problem, right? If you plug 83 back into the original equation, right, 83 minus 2, right, is going to equal 81. And that's not going to make the argument negative. So that's all you need really to check. You don't need to check to see if it satisfies the original equation entirely. It should, right? But I'll show you in a further example later on that when the domain, or sorry, when the argument becomes negative, you know to exclude it. Okay, so this is going to check. You can plug it into your calculator just to see that this entire equation is going to be true. All right, so moving on to example number 3. You know, what if you're given something like this? ln of x squared plus 3 minus ln of x minus 1 is equal to ln of 7. Okay, so what I don't want to see in this problem is don't do this, okay? When students see this, they're like, oh, use the inverse property. They're like, oh, e to the ln of x squared plus 3 minus, you know, e to the ln of x minus 1 is equal to e to the ln of 7, right? Because that's what you said, Mrs. Zhu. You know, that cancel, and you have x squared plus 3 minus, you know, x minus 1 is equal to 7. Okay, this is not true. You cannot do this, all right? Why can I not do this? Didn't you do it on the previous problem? Well, if I look on the previous problem, right, notice the only time you can use your inverse property, right, is you have a single term or a single log, I should say, and then you have some kind of constant. That's the only time you can use the inverse property. Right now, this is not a single log, right? Exclamation mark, right? And so you cannot exponentiate all 3 sides by base e. All right, so again, this is incorrect. Don't do it this way. I've seen students make up rules over the years. Please don't do this on your Chapter 3 exam. Okay, so what is the correct way? What is the correct way? Well, you said, Mrs. Zhu, to condense it, right? You have to have a single log. And so the way you have a single log is to condense. So this left side of the equation, right, what I could do is write ln of x squared plus 3 over x minus 1, right? I condensed it, is equal to ln of 7, right? X squared plus 3 minus x minus 1 is using the quotient property. Again, you write the word ln one time. And now, right, if I go all the way back to my guideline number 2, right, my one-to-one property says that if I have a single log and a single log of the same base, and this statement is true only if the arguments are equal to each other, right? And so basically on this problem, I have ln on both sides, right? They both have the same base. All I have to do right now is just set the arguments equal. And that's it. You don't need to do anything else other than that. Okay, so condense into a single log, then you could use your one-to-one property on this particular problem. Can you exponentiate both sides by base e now? Yes, you could. Okay, so you could do this, or you could say e to the ln of x squared plus 3 over x minus 1 is equal to e to the ln of 7, right? I mean, sure, you can do it now. You can do this or this. Either one's fine. Okay, so if you went directly from here to here, you're using the one-to-one property. If you do it like this way right here by exponentiating base e, right, this is okay as well. Okay, you'll still get the same equation. All right, so that's it for logs, right? From here, you do a little cross multiplication to solve. You're going to get x squared plus 3, right, times 1, which is just x squared plus 3 is equal to 7x minus 7. Again, you have to practice your quadratic equation skills, right? Move the 7x over. 3 plus 7 is equal to 10. Is equal to 0, right? You have x minus 5, x minus 2, and you're going to get two solutions. X is equal to 5 or x is equal to 2. Now make sure you check 5 and 2 back into the original, right? If I plug in 5 into my argument here, 5 squared is 25, 25 plus 3 is 28. That's not going to make the argument negative, so I'm okay over here. 5 minus 1 is 4. That's also not going to make the argument negative, so I'm good. Likewise, if you plug in x is equal to 2 back into the original equation, 2 squared is 4, 4 plus 3 is 7. That's not negative, and 2 minus 1 is 1. So I'm good. Okay, so both of these are going to check, and I'm done with that problem. Okay, so just be aware, please don't do this, okay? Condense it and then use the one-to-one property. The only time you can exponentiate is, notice I have a single log and a single log or a constant term, then you can use the inverse property, okay? So you can't just do it right from the beginning. So please pay close attention to the details. Okay, moving on. Example number 4. What if you have log base 5 of, y minus 12 plus log base 5 of y plus 12. Okay, so again, I'm going to state this again just to make a point. Cannot do, okay? Don't say, oh, this is just 5 log 5 of y minus 12 plus 5 log 5 of y plus 12, right, is equal to 5 squared. This is not true, okay? Please don't do this. Again, you have to have a single log, okay? So when can I do that? Let me go back to example number 1. Notice on this step right here, back to example 1, right? This is a single log on the left side of the equation. And then on the right side of the equation, there's a constant. That is when you can exponentiate both sides by base 3 or use the inverse property. Okay, so single log, constant term, or single log and single log on the other side. That's the only time you can use the inverse property. Now, back to this, right? This is not a single log, right? I need to condense into a single log. Right, that's why you had all those condensation problems. So why don't you do that? So this is the correct way. From here on out, this is the correct way. Condense. When you have the sum of two logs, right, it's the product of two logs. So hopefully you can do this in your head. Y minus 12 times y plus 12, right, that's sum and difference pattern. That's y squared minus 144 is equal to 2. Now, right, you have a single log. Notice you have a single log and you have a constant, right? Now you can use your inverse property, okay? That's when you can do it. So it took me many years of experience, right? To accumulate years of experience to be able to pick up on this, students making the same type of mistakes year in, year out, okay? All right, so whatever you do to the left, you do to the right, exponentiate by base 5, right? This cancels out. You're going to get y squared minus 144 is equal to 25. Y squared is equal to 169. When you take the square root, make sure you write positive 13, right? Or y is equal to negative 13. Okay, now you have to check both of these answers. Y equals positive 13. If I plug it back in, 13 minus 12 is 1. So I'm good to go over here. It's a positive number. 13 plus 12, that is 25. Okay, so in fact, if you condense it, you should end up equaling 2, right? Because log base 5 of 1, 5 raised to what power gives you 1? That's going to be 0. Log base 5 of 25, right? When you plug in 13 over here, that's just 2, right? 2 plus 0 is equal to 2. So this actually checks, right? Now, if you plug in negative 13 into the original argument, right? In fact, this one, let me write it out here. If you plug in negative 13, you're going to get log base 5 of negative 25, right? Plus log base 5 of negative 1 is equal to 2. Not possible, right? You can't have a negative within the argument of a logarithm, right? 5 raised to what power gives you negative 25? There is nothing, right? 5 raised to what power gives you negative 1? There is no number. So this is my extraneous solution that I was talking about in the beginning of the lecture. So the only answer is y